Hello everyone, my name is Ian Rosens. Today I'll be proposing a research project on the failure and fragmentation of ceramic targets after multiple ballistic impacts. Armor on light military vehicles usually contains layers of ceramics designed to stop projectiles and fragments from penetrating. They must erode the projectile and absorb energy. Specifically, on armor arrays containing ceramics consist of layers of protective materials to stop projectiles from perforating, while ceramics fragment during impact, which limits the effective protective abilities after repeat impacts, resulting in low toughness and reliability. On the image to the right, you can see various layers of different materials, potentially ceramics, in an array. Now, ceramics are mainly ideal due to their weight efficiency, and ceramic arrays are far more weight efficient versus steel or similar malleable metals and alloys. Ceramics in arrays usually contain a layer of ceramic itself to damage the projectile, reduce its velocity, and deform it to reduce the penetrator's abilities to damage the intended target, while a backing layer secures the ceramic tile and finally stops the projectile. It must be malleable and may deform a marginal amount to absorb energy and fragments from the projectile. Now, ceramics have high hardness. This is the resistance of a material to permanent deformation and allows the plate to absorb more energy. This also results in low fracture toughness and shattering in the area local to impact. On the image to the right, you can see a projectile and fragments leaving the rear face of a plate due to the high hardness of the material, resulting in a high transfer of energy from the projectile into the plate. Now, when compared to steel, ceramics usually have a density of around 3.85 grams per cubic centimeter, while steel's density is about 7.85 grams per cubic centimeter. And steel is much denser than ceramics. And also, when compared in the ability to transfer energy, ceramics have a modulus of 370, while steel's is 210, where a higher number is a stiffer material, basically meaning that ceramics will absorb more energy from a projectile. Finally, ceramics fragment, shattering into smaller shards. Now, the impact velocity is the velocity at which a projectile impacts the target. Ballistic limit is the minimum velocity where a specific projectile may perforate a specific target, and the V50 is the velocity where a projectile penetrates the target half the time. The other half the time, projectiles fail to fully penetrate. They lodge in the target, fragment, or ricochet. In Ben Doradal's study, cracks rapidly propagate towards edges of the ceramic, and in Sarvastani et al.'s study, plates catastrophically fail after multiple impacts as the ceramic is weakened. This means there's limited information on repeat impacts at the same point and the paths of fragments after impact. Problem is that around the V50 ballistic limit of a plate to a given projectile, the plate will fail half of the time. When the plate doesn't fail, the penetrator is stopped and the plate is substantially weakened. On the right, you can see what a projectile might look like lodged in a plate after a non-penetration. You can see that layers of the composite in this case have split apart and have weakened the plate because of this. So our guiding question will be, to what extent will ceramics plates be weakened after an initial ballistic impact? And the goal will be to perform ballistic tests in order to examine the degradation of a plate over 2 impacts. So first we'll build a launcher to use as a testing device. Now, both the launcher and mount will be constructed by myself, and I will construct a single frame for the entire apparatus. Now on the diagram below, you can see the lasers and receivers for a light gate. The projectile will block each pair of lasers and receivers beams, and this will allow us to find the distance traveled over a certain amount of time, allowing us to find the velocity of the projectile. Now, for the initial set of tests, one single pressure for the first stage of the experiments coordinating with a single velocity will be set, allowing us to have a benchmark velocity for the projectile. and in this case, a lower pressure will result in a higher velocity, as the projectile will be contained in a chamber at about -2 atmospheres, meaning that when the rear end cap is perforated, the air will rush into the chamber, forcing the projectile forward, past the light gate, and eventually into the intended target. Now, this diagram is not to scale, but it's a good way to show the actual process of the launcher. Now, the intended projectile to be used in this experiment is a 50 caliber 12.7 millimeter Browning machine gun projectile, or BMG. It's a steel projectile, and it will be encased in a 40 millimeter discarding sabot mounted in the launcher. Sabot suspends the projectile in barrel and allows for a higher transfer of energy for a smaller round. Sabot in this case will be composed of resin. Now, initially, will impact targets around the predicted limit velocity according to external sources. For narrow testing beyond that, we'll find the specific V50 of the plates. Since they're non-ductile brittle targets and thin sheets of alumina, fragmentation will be mainly recorded in these later studies. So we'll be examining failure and fragmentation patterns. Multiple impacts on each individual plate will be performed at or roughly below limit velocity, as limit velocity is based on the bore velocity. Now, 2 impacts at the same point in the plate will be done, and the key factors that will be recorded after each impact will be the dimensions of the crater created by the projectile, cracking patterns, whether the target was perforated or not, fragments velocity, especially spall, fragments coming up from the face of the plate, scabbing, fragments ejected behind the plate but not by the projectile, finally fragments of the projectile and from the projectile itself. Also look qualitatively at the mass and shape of fragments, take fragment samples. We'll also erect a paper sheet behind the target to see the practical effect on a rough simulation of a person. And we'll also take the dimensions of each individual target plate, the mass of the plate, the temperature at the time of both the plate and of the surroundings, and finally the exact vacuum pressure before each launch. Now, during the initial impact, we'll expect large cracks, moderate penetration, moderate spall, and mild scabbing, meaning that the projectile will not fully perforate the plate, only lodging itself in the plate. During the secondary impact, the plate will fully fail, as the projectile will go all the way through the plate, fully perforating it, and fragments from the rear will have high velocity, and the paper will obviously be very damaged. Now, this background will allow for future experimentation to find the precise effect of an initial projectile on weakening an armor plate for a secondary projectile. And the 40mm sabot and testing rig will also be useful for future experimentation. On the right, you can see the sabot, which is in the process of being designed by myself. This is the version 1.0. Now, in terms of expected limitations, the initial experiment only examines one specific circumstance at a specific velocity, and the V50 inherently requires twice the initial testing subjects to complete the second set of impact trials due to the inherent qualities of the V50. Finally, sabot petals may damage the target if they haven't flown away in time. Now, in terms of future testing that could be done, we could find the relationship between an initial impact's effectiveness at weakening a plate at various velocities, and also find how the initial impact affects the second over distance. We could also adapt the 40mm sabot for commercial use, or examine the same factors with other ceramics and resins and brittle materials other than alumina to see different fragmentation patterns from the same set of tests. Here are my references. I'd like to thank Dr. Randall for his advisement and assistance, and to Mr. Prendergast. Do you have any questions? Thank you for listening.